Hello, my name is Jared Skeens and welcome to the Zoom room. Today we want to look at Pure Math 3, Transcendental Functions, Part 7, Trigonometry with a focus on this a sine x plus or minus b cosine x form, derivatives and integrals of the trigonometric functions. So first, we're going to start off with this unique kind of form here. And there are two different ways that this form can occur. It can occur with the sine in the front and the cosine in the back, or it can occur with the cosine in the front and the sine in the back. So if it's a sine x plus or minus b cosine x, where a and b are coefficients, then that can be converted into this r sine of x plus or minus alpha. And the plus or minus are in the same order as this plus and minus here. So if this is plus, this one's plus. If this one's minus, then this one is minus. Also, and very similar, if the cosine comes first, then you have a cosine x plus or minus b sine x, then that can be converted into r cosine parentheses x minus plus alpha. So notice your plus and minus get switched over here. So if it's positive in this form, it's negative in here. If it's negative in this form, it's positive here. So the only difference here is whether sine is first or cosine, and whichever one comes first is the one that it's kind of condensed into. So kind of condensed into one trigonometric function instead of two. Another similarity is that both of them have this r coefficient in the condensed form, and they also have this alpha that makes it a sum or difference identity basically within this condensed form. Now, these are not in the formula guide provided by Cambridge, but you don't have to memorize them, at least this up here, because they're already stated this way in the Cambridge questions, and you'll see as we get into the examples, they provide you with the form that you're starting with, and they also tell you which form to transfer it into. So these are provided for you within the question itself. What you do need to memorize are these two asterisks here, how to find the r and then how to find the alpha. So the r is very easy to remember. It's just basically the Pythagorean theorem with a and b, and the a and b are just your coefficients on the trigonometric functions. So the square root of a squared plus b squared is your r. And then to find the alpha, you do tan alpha equals the b over the a. Now the b and the a, or the a and the b, are the first and second coefficients in that order. So the b over a, the b is always the second coefficient, so it doesn't really matter the trig function. It's the second coefficient divided by the first coefficient. And then, of course, to solve for alpha, you have to do the inverse tangent. So whether you want to write this one out here, or both, or just this one here, you find alpha by taking the inverse tangent of b over a. And you don't have to pay attention to the signs as in positive or negative, because you are limited to the first quadrant anyway, and all trig functions are positive in the first quadrant. So just ignore the plus and minus when you're working with the b in the alpha part. And in this part, it doesn't matter either because you're squaring the a and b, so either way they're going to come out positive. So you don't really have to worry about the signs except to make sure that you get the correct one written here in the condensed form, which if you're paying attention to the question in the Cambridge question, as it provides it for you, then you'll get it right anyway. Okay, so this is what we're going to work with here, and I'll set up for us our first example. Okay, let's look at our first question that we have here. Take you to the share screen so you can see it for yourself. Notice the code up here if you're interested in where it's from. It says express root 6 sine x plus cosine x in the form r sine x plus alpha, where r needs to be greater than 0 and alpha is between 0 and 90 degrees. State the exact value of r and give alpha correct to 3 decimal places. So we'll come back to the board. And here we see, here is the original form, our a sine x plus or minus b cosine x form, root 6 sine x plus cosine x, and we want to transform it into this condensed form of r sine of x plus alpha, and we need to find the r and we need to find the alpha. The r needs to be exact, meaning no decimals, keep it as a radical, and the alpha needs to go to 3 decimal places. So the first thing we want to do is we want to find our r. Our r is the square root of a squared plus b squared. So root 6 is the a, and understood 1 is the b. So that gives us a square root of 6 plus 1. It's root 6 squared, so that's just 6. 1 squared is 1, so that gives us a root 7 for the r. And then for the alpha, we do the inverse tangent of b over a. b is an understood 1, a is the root 6. And so when we get this one, we get our alpha is equal to 22.208 degrees. Then we can write out our answer here. And we have plus because it's plus here, plus here. When sine is in the front, the signs stay the same as what they were. And if it's cosine in the front, they switch. So plus our alpha is 22.208 degrees. And this here is our answer for this one. Okay, I'll set up another one for us. Okay, for our second example, pull it up here so you can see it. Again, this is from Winter 18, paper 31, number 6. Show that the equation root 2 cosecant x plus cotangent x equals root 3 can be expressed in the form r sine x minus alpha equals root 2, where r is greater than 0 and alpha is between 0 and 90 degrees. Okay, so in this one, it's the same thing as what we did before, but they've just added a little twist to it. They've given us the reciprocal functions. So we've already talked about the reciprocal functions back, I believe it was in part 4, where we first started the trigonometry part of transcendental functions. And so what we need to do is we need to kind of rearrange this with our reciprocal functions and get it back into this original format here. Then we can transfer it into this final condensed form. So our cosecant is 1 over sine x. So we get root 2 over sine x plus, and then cotangent is 1 over tangent. Tangent is sine over cosine. So this is cosine x over sine x. That's cotangent equals root 3. So what we want to do here is we want to get rid of our denominator. So we're going to multiply everything through by sine x. And what we get, the sine x cancels. Here's our root 2 plus cosine x equals root 3 sine x. Then we want to get it up into this form up here. And we want the sign to be in the front because sine is what we get in the condensed form. If it was cosine in the condensed form, then we would want the cosine in the front. So we want this, the sign in the front, so that's root 3 sine x minus the cosine x, that's what's going to give us the minus here, and then equals the root 2, and we can see the root 2 already right there. So now after we've done that little bit of rearranging with our reciprocal functions, we now have it into the proper form so that we can now do this part here. So to find the r, our square root of root 3 squared plus, this is an understood 1. You can put -1 if you want. It's not going to matter because you're squaring it. And so you get root 3 plus 1, which is root 4, which is 2. And then our alpha is the inverse tangent of b over a, 1 over root 3. You don't need the negative sign because we only want a first quadrant answer, which is the positive quadrant for all the trig functions. And when you do 1 over root 3 inverse tangent, you get 30 degrees. And so we end up with a final condensed form here of 2 sine of x minus 30 degrees equals 2. Now it does show up as an equation. What I didn't show you on the last problem, and I won't go back to the last problem, but I'll just show it to you here on this one. And that is what we're working on is the part I. There are follow-up questions to these that are usually solving. So we've already done solving in a previous video. So if you're interested in the solving part, then go back to, I think it was video number 6 was the solving. If you want the identities, that would be video number 5. So, so there is a follow-up question, but we've already covered that. You should be able to solve it from here. We're just working on the changing of the form right now. And so we'll do one more example, and then we'll get into the derivatives and integrals. Okay, here's our last example for this particular part. And it's from summer of 17, paper 31, number 8. By first expanding 2 sine x minus 30 degrees. So in other words, we need to expand this difference identity, or using the difference identity, express 2 sine x minus 30 minus cosine x into the form r sine x minus alpha, where r is greater than 0 and alpha is between 0 and 90. Give the exact value of r and the value of alpha correct to 2 decimal places. Okay, so again, we have a little twist. We need to first use an identity. So here is the full form, but we need to expand this part first. So when we expand that, we have this 2 in the front, and then we have the difference identity, which is in your formula sheet. So look up the formula sheet, and you get sine x cosine of 30 degrees minus cosine x and sine of 30 degrees. That's the 2 times all of this. And then we have this minus cosine x here at the back. So don't forget that. Now we can do our exact values. So to do exact values for trigonometry, use our special triangle. Here's our 30, 60, 90 right triangle with the ratio of 1, 2, and root 3. And so cosine of 30 means we're coming from the 30 degree mark. Adjacent over hypotenuse is root 3 over 2. And sine of 30 opposite over hypotenuse is 1/2. So when we multiply the 2 through, it cancels out the 2 in the denominator, so we get root 3 sine x. Cancels out here, so we just get minus cosine x, or minus cosine x, and then minus cosine x again. And now that we have that, we get root 3 sine x minus 2 cosine x. Now we are in the form that we want to be in after simplifying that. And so this will become, and so we need to find the r. So the r will be the square root of root 3 squared plus 2 squared. Again, doesn't really matter whether you put the plus and minus with it or not, because they'll both come out positive. So that's root 3 squared is just 3, 2 squared is 4. So we end up with a root 7 as our exact value for there. This is going to end up being a sine x minus alpha. Now we got to find the alpha. So the alpha is going to be the inverse tangent of b over a. Again, you don't need the negative, just the 2 over the root 3. You don't need the negative because we always get first quadrant answer for our alpha. And our alpha, when we do this, comes out to 49.11. To 2 decimal places. So 49.11 degrees. This right here is the answer that we're looking for. So these aren't too bad to do. They give you basically the setup in the problem, and they also tell you the condensed form that they want it to end up looking like. You just need to remember how to find r, how to find alpha, and as we saw, they threw in some reciprocal functions that you had to deal with. In this case, an identity that you had to expand first. But all in all, they're not that difficult to do. They don't show up on every question set in Cambridge exams, but they do show up probably in every yearly set. So they don't always show up in every individual test, and they might not even show up in an entire series, but sometime in the whole year, like the May, June, or October, November, it usually does at least show up once. So be ready for that. Now what we want to do is we want to look at derivatives and integrals. Okay, for this section on derivatives and integrals, we're not going to actually do any Cambridge problems yet. What I'm going to do is just teach you the basic derivatives and integrals for the trigonometric functions as an individual term. After this unit of transcendental functions, we move into the derivatives unit, and the first thing we get into in the derivatives unit is the product and quotient rule. The product means you're multiplying two different terms that have an x in it, and the quotient is, you're dividing two different terms. And those terms can be a mixture of algebra, logarithms, exponentials, trigonometric functions. So in order to do those product and quotient rules, you first of all have to know how to do the derivative of an individual term. And in Pure Maths 1, you already learned how to do the derivative of an algebraic term. And then earlier in the transcendental functions, we looked at derivatives and integrals of your exponentials and of logarithmic functions, or at least the e to the x and ln x. Okay, so we're going to do that with the trig functions, just so that you know the basics which then you'll be applying in the questions in the next unit. So the first thing we're going to look at is derivatives, and just a little bit later we'll look at integrals, which I haven't written down yet. So for the derivatives, basically they're all in your formula sheet. If you look at the formula sheet, all the derivatives are listed. Anytime you're doing derivatives or integration, you should have your formula sheet right there handy so that you can find what you're looking for very quickly. But if there's anything that you're going to memorize these two. These two are the fundamental ones here. The derivative, which is d dx, that's our kind of our notation for taking the derivative of sine x is equal to cosine dx, cosine x dx. Okay, so sine x, the derivative of sine x becomes cosine x dx. Dx is the differential, and we'll talk about differentials again later in another unit. And the derivative of cosine x is a negative sine x dx. Now again, if you're going to memorize things, these two you should memorize. You see them so frequently, and you'll use the rule so often that I'm pretty sure you'll have it memorized in no time anyway, because you'll be constantly doing them. And but from these two, everything else comes out of that. For example, tangent. Tangent is actually a quotient, sine over cosine. So later, when we get to the quotient rule, you can actually start with tangent being sine over cosine. You can do the quotient rule, and you'll end up with secant squared x. You can look in your formula sheet and see that derivative of tan x is secant squared x. So these two here are the most fundamental. These three here are your basic trig functions. But tangent and the reciprocal functions, like cosecant is 1 over sine, secant is 1 over cosine, cotangent is cosine x over sine x. All three of those and tan x are fractions. They are quotients. So you can actually apply the quotient rule to tan x and the three reciprocal functions and derive their derivatives. But like I said, they're in the formula sheet. You want to work efficiently, and so you'll have to figure out what you can remember and what you need to look. For this one down here, the derivative of inverse tan x, I'm not sure why they only chose one out of all of them, but for the inverse functions, you only need to know one of them. This is part of the new syllabus material in the 2020 syllabus cycle. So this wasn't in the old curriculum set or the old syllabus set. And again, it's in the formula sheet. So the inverse tangent of x, the derivative of that is equal to 1 over 1 plus x squared. What you're going to find out is this x and x squared, this creates a pattern that you're going to be identifying as what is in the position of that x. It might just be x, it might be expanded a little bit. So just follow your formula guide and follow the pattern that's established with that. And because it's new to the syllabus, there's not a lot of practice questions, although you can find it in the specimen paper for that. Now, what we want to do is look at an example of what you would have to do with deriving a trig function. This gave you just the trig function itself, okay? The bare basic trig function. Sine becomes cosine, cosine becomes negative sine. That's your most basic trig part. But when you're dealing with a trigonometric term, there's three things that you need to consider. First, the exponent. Second, the trigonometric term. Third, the argument on the inside. So when we derive this, so we have d dx, the derivative of this trigonometric term. The first thing that we want to do is notice the exponent. So we're going to follow this just like we did in the algebraic term. We multiply the exponent to the front, becomes 6. We subtract 1, and so this just becomes 6 sine with an argument of 4x. So the 2 multiplied to the front and subtracted 1, just like in an algebraic term, we did the same thing with the exponent there. And so 2 times 3 is 6, 2 minus 1 is an understood 1, and the trig function does not change for the exponent step. Then the second thing that we want to do is the trig function itself. This is the second thing that you want to look for. And the derivative of sine is cosine. So now we have multiplied onto the end of that a cosine for x. The argument doesn't change. So in our exponent step, the trig function did not change. Now in the trig step, the argument does not change. Then the third thing is we need to look at the expanded argument here. And that is, instead of just an x, it's now a 4x, and we need to do the derivative of the inside, which is another product of 4, multiplication of 4. So this gives you a total of 24 sine 4x cosine 4x. And that would be your answer to this particular derivative. And this is just one term. Okay, so this is what you kind of need to pay attention to, whether you're dealing with logarithms, the expanded algebraic terms, or the trigonometric terms. Start with the exponent, then do the transcendental function, then do the argument. Okay, so in algebra, we did the exponent first, and then we did the derivative of the expanded part on the inside. With transcendental functions, we do the exponent first, then we do the transcendental function, whether it's logarithm or exponential or trig, then the expanded part for the inside. So here's the first part right here. Here's the first part, here's the second part, and there is the third part. Combine it all together, that's your derivative. And in moving forward into the derivative unit, you'll then start putting that together into these product quotient formulas where you're doing the derivatives of a couple of different terms at the same time. So this is how you do the derivative for that. And I will set up for us the integration part. Okay, just before we get to the integrals part, I wanted to show you the specimen paper for that new material. So this is from the specimen paper of 2020, and in number 5, it has this derivative of x. Show that the derivative of x minus the inverse tangent of x equals x squared over 1 plus x squared. This is, I identified it as part of new material in our 2020 syllabus cycle. So first we do the derivative of x minus the inverse tan of x. So when you do the derivative, you just do the derivative of the individual terms. The derivative of x is just 1. You should have learned that in the P1 math book. And then what we just saw a minute ago, the derivative of inverse tangent of x is 1 over 1 plus x squared. And then from here, it's just algebraically getting a common denominator and combining like terms, and then you end up with the x squared plus 1 over x squared. So again, you don't really have to memorize it. You just need to look it up in your formula sheet, plug in the correct formula, and then continue on with the question. Now let's go back and look at integration, and integration goes the opposite direction. So what what I like to say is you can't integrate, or you can't go backwards. Integrating is kind of going backwards. It's the opposite direction. You can't go backwards unless you have a going forward. You can derive just about anything, but you can't integrate everything. You can only integrate it if there's a going forward to that point, then you can go backwards. Now, what does that mean? It might be a little confusing for some of you. So let's look at the derivative. Here's cosine x. The derivative is a negative sine x. So because we end up with a sine x going forward, then that means we can go backwards. So you can't go backwards unless you have that going forward. Okay? So the integral of sine x then, put the negative on the other side, and you get a negative cosine x plus c. Don't forget the plus c, which is when you have an indefinite integral. You don't have bounds of integration. You need to put the plus c. So the integral of sine x, you're just going backwards, and you get negative cosine x plus c. When you derive sine x, you get cosine x. So because we have a going forward, then we can go backwards. So the integral of cosine x dx is sine x plus c. Easy. Well, notice with tan x, the derivative of tan x gives us secant squared. We don't have the tan x as the end result of the derivative. We don't end up with a tan x going forward. Therefore, we cannot integrate tan x and go backwards. We can integrate secant squared x because it was the result going forward. So the derivative of tan x is secant squared x. So we can integrate secant squared x and get back to tan x plus c. So notice we can derive sine, cosine, tangent. We can derive or do the derivative for any basic trig function, inverse reciprocal trig function, even the inverse trig functions, although you only need to do one. But for integrating, you can only integrate the ones that showed up in the result of the derivative. So because sine showed up, we can integrate that. Because cosine showed up, we can integrate that. And because secant squared showed up, we can integrate that. But we cannot integrate tangent with what we've learned up to this point. Okay? So again, use your formula sheet to help you. Derivatives are usually pretty easy to do. The going backwards with the integration is sometimes a little bit more difficult to follow. So use your formula sheet to help you out. Then we get down here to the inverse trig function. Notice the derivative of inverse tangent is 1 over 1 plus x squared. So when you integrate that, you have to recognize that this is not your integration of algebra. This is a special pattern. This special pattern, and notice this a squared is this 1 over here. That's why I put a little arrow here. You don't recognize that 1 as being, something of a pattern, but it is. Whatever is there, a squared is that location plus x squared. So if this is a 4, this would be like a 2 squared kind of thing. Or a 4, you change it to 2 squared. And then when you integrate this algebraic pattern, you get back to your inverse tangent, and you have 1 over the a as your coefficient, and you have x over a as the argument of your inverse tangent, and then of course the plus c at the end. So when you get to this pattern, at least recognize it. Go to your formula sheet. Anytime the Cambridge question asks you to integrate something, go to your formula sheet, look for what fits the pattern. This is the only one that you have to do that really has the algebraic function for your inverse trig function, or your algebraic for your inverse trig function. There is an algebraic one for ln, the 1 over x. So those are the ones that are a little tricky because they're not obviously logarithm or tangent. They look algebraic, but they're not. So when you integrate it, it goes back to that transcendental function. So again, familiarity with your formula sheet is most important, especially since they give you the formulas. You don't have to memorize it like some curriculum make you do. And that is wonderful. You just get to execute what it is that they want you to solve. So that's the end of transcendental functions. And we've looked at exponentials, logarithms, we looked at trig functions, derivatives and integrals of all of them, at least on a one-term basis. And so thank you for joining me. I hope you join me again as we begin the next unit on differentiation. And I look forward to seeing you